Okay. Hello guys, welcome back to another video, and today we're going to be talking about Ohm's law explanation questions. Now, in my experience of teaching international GCSE physics, this is a topic that most students struggle with, not because they don't understand Ohm's law in particular, but because they're not taught the specific steps that they need to take to be able to answer these kind of questions. And most students, when they do pass papers, because they're really focused on finishing the questions and finishing the papers, they don't really pause and analyze the mark schemes and create a kind of strategy to solve such kind of repeated questions. So what I want to do in this video is I want to provide you guys with a structured step-by-step approach to answering any kind of question that involves explaining the changes in the circuits using Ohm's law. So the type of questions that we see in international GCSE physics are questions where you have to explain how the current changes when there is a change in the resistance, or how the voltage changes when there is a change in the current. And rarely you have to explain how the resistance changes given that there is a change in the current. And I have roughly separated the questions into two categories. The first category is the type of question where you have to explain the changes taking place when the structure of a circuit changes from a parallel circuit to a series circuit. The second type of question is in circuits where there is a fixed resistor and a resistance changing component. So we could be looking at things like variable resistors. We could be looking at thermistors, and we could also be looking at light-dependent resistors. Now, in these kind of questions, when we're changing from a parallel to a series circuit or vice versa, we're going to have to set voltage as constant. And that's because we're going to be looking at the changes within the circuit, not across a particular component, but we're going to be looking at the changes to the current and the resistance going through the battery or of the entire circuit. However, when we're looking at the circuits where we have a fixed resistor and a resistance changing component, we're going to have to set R as constant. And that is because we are going to be using the fixed resistor as a link to understand how the voltage across the resistance changing component changes, or simply to look at how the voltage across the fixed resistor itself is going to change. Now, the first thing that we need to know before we look at the step-by-step method is, of course, the idea of combined resistance. In a series circuit, combined resistance is simply the sum of the resistance of the individual components within that series circuit. So in this example, we have R1 and R2. So if we want the total resistance of that, we simply add them up to get RT is equal to R1 plus R2. However, in a parallel circuit, the total resistance of the circuit is not as simple. So if we want to find it, the reciprocal of the total resistance is going to be equal to the reciprocal of each individual component added together. Now, what is the implication? And by the way, you do not need to know this formula for your Edexcel International GCSE Physics. You do not need to make calculations with it. But however, you will need to know this in order to make calculations. That the combined resistance in a series circuit is going to be the sum of the resistance of each individual component. Now, what is the implication of this? Well, take a look at these two circuits. We have R1 and R2. And in both circuits, R1 and R2 are exactly identical. In such kind of scenarios, the parallel circuit connecting those two components will have a lower total resistance because of this equation. You do not need to know the equation, you just need to know its implication. What is the implication? It is that the circuit in parallel will have a lower total resistance. Cool, now we know this. And by the way, why do parallel circuits have a lower total resistance? Well, that's because there are more paths through which electrons can flow. And this is the exact wording that the marking scheme uses when we're explaining the difference in the total resistance between the parallel and the series circuit. In a series circuit, there is only one path. And because there is only one path, the traffic is high. However, in a parallel circuit, we have more than one path, and so electrons can flow more freely, which is why in a parallel circuit, the total resistance is much lower, allowing for a higher current. Okay, so let's take a look at this scenario. Here we have this series circuit, and we're going to connect the same two components in parallel. And we have to explain how the current through the battery changes when those two resistors are connected in parallel instead of series. Of course, the first step is to imagine or to write down the equation V is equal to IR somewhere on your answer paper. And the first thing that we know is that the voltage across the battery, or the voltage supplied by the battery, remains the same. So that is the first thing we think about. The voltage supplied by the battery is the same in both scenarios. And therefore, in our equation, we can set V as constant, allowing us to form an inverse relationship between current and resistance. And of course, when we say current, it is going to be the current through the circuit. It's not going to be the current through R1 or R2, but the combination of that. So it's going to be I total equal to I1 plus I2, excuse my handwriting here. But in this series circuit, it's simply going to be I2, and it's going to be the same as I1 and I2 because in a series circuit, there's only one current. Okay, anyways, back to our steps. So first of all, we know that the voltage supply is the same. Okay, now let's take a look at the resistance. So we're going from a series circuit to a parallel circuit. How does the total resistance of the circuit change? How does the resistance that the battery is dealing with change? Well, in the parallel circuit, we have more paths. And when we have more paths, electrons can flow more freely. And therefore, in the parallel circuit, we have a much lower total resistance. And because the circuit or the battery is working with a lower total resistance, the current going through the battery or the current through the circuit is going to be much higher. And when we explain, or when we write the explanations, we state because V is equal to IR, or you can rearrange the equation, which I prefer, and say that because the voltage is constant, as the resistance has decreased, the current will be able to increase. Now, if you have difficulty with looking at the change in the voltage and the current, I like to imagine the two components as a single component. So across this single component, the voltage is the same because it's the same battery. However, this single component has much lower resistance than this component because this one is composed of R1 and R2, but those R1 and R2 resistors are in parallel. However, here, those R1 and R2 are in series. So the resistance of this component is going to be much higher than this. And therefore, the current going through that component is going to be much higher because of a much lower resistance. So that's how I like to imagine, or how I like to approach, having these two resistors connected in parallel. I like to think of them as one component. I like to think of the two resistors in series also as one component. And I like to think of them as having different individual resistances. So the total resistance becomes the resistance of that single component. Okay, now let's take a look at the inverse. What if we change from a parallel circuit to a series circuit? So it's going to be the opposite. The resistance is going to increase because in a series we have fewer paths, and because the battery voltage is the same, the current is going to decrease. And by the way, this little quote, when the resistance doubles, the current halves. Now I put this because in some questions, they want you to make explanations quantitatively. Even if it's not in like exact numbers, they want you to, they give you an extra mark when you say the resistance doubles instead of saying the resistance increases. And as we can see from the Ohm's law equation, the resistance and the current are going to be inversely proportional due to the voltage being constant. And so the amount by which the resistance changes is going to be completely opposite to the amount by which the current changes. So if the resistance is going to be double, the current is going to be half. If the resistance is going to be 4 times, the current is going to be decreasing by a quarter. Okay, So that is pretty much it for the questions where we are changing from a parallel structure to a series structure and vice versa. Let's now take a look at the questions where we have a fixed resistor with a resistance changing component in a series circuit. Now, these are the type of circuit structures that we're going to see when it comes to these kind of questions. Here, X represents the component whose resistance can be changed. So we're talking about, of course, a variable resistor. We're talking about thermistors. We're talking about light-dependent resistors. It could be any of them. So what kind of questions can they ask in terms of this circuit structure? Well, they could ask, okay, when the resistance of component X changes, how does the voltage across the resistor change? And they could also ask by going a step further, how does the voltage across component X change? So for this type of question, we're going to have to take an extra step to answer how the voltage across component X changes. So let's take a look at these steps. So first of all, we're going to have to state how the resistance of the component X changes. In some mark schemes, they don't give a mark for that, but this is very crucial. In order to be able to answer the question further, we need to start from here. Because for example, if they give us a, let's say, thermistor, well, we don't know how the resistance of that is going to change unless we think about the relationship between temperature and the total resistance, and we use the change in temperature to find how the resistance changes. So as the temperature increases, the resistance is going to decrease, and as the temperature decreases, the resistance is going to increase. So we need to be looking at how the external conditions, such as the temperature and the light intensity, changes, and we need to use that to find how the resistance of the thermistor or the light-dependent resistor changes. We need to find that out first. Secondly, how is that going to have an impact on the total resistance of the circuit? Now, in a series circuit, we've said that before, the total resistance of the circuit is going to be the sum of the resistances of each individual component. So in this particular example, we have R1 and X. So if we want the total resistance, it is simply going to be R1 plus R of X. Now, when the resistance of X changes, it is going to have a direct impact on the total resistance. So assuming that the resistance of X decreases, the total resistance is also going to decrease because it is a sum. If the resistance of X increases, the total resistance is also going to increase because it is a sum. So it's basically a direct effect. Okay, so once we know how the total resistance changes, we can now take a look at how the current through the circuit changes. Now, the battery supplies voltage, and that voltage is constant. And so if we take a look at current and resistance, they're going to have an inverse relationship. So in our previous example, let's say that the resistance across component X decreases, and thereby the total resistance of the circuit decreases. Now, if the total resistance of the circuit decreases, the current is going to increase. So there is less resistance, the current can flow more freely. But if the total resistance increases, the current is going to decrease. Now, that is the third step that we need to take when we are answering these questions. When the total resistance changes, how does that impact the current through the circuit? And then we take a look at the voltage across a fixed resistor. Now, the reason we take a look at the voltage across the fixed resistor instead of going straight to the resistance changing component is that for a fixed resistor, it has constant resistance. And because resistance is constant, we can immediately find the directly proportional relationship between voltage and current. Whereas for the resistance changing component, even if we write V is equal to IR, we still cannot form any kind of relationship between V and I because R is not a constant. It is also a variable. So we have three variables, we can't work with that. Which is why we go to the fixed resistor where we have a constant and two variables. Cool. Now, the voltage across the fixed resistor is going to depend on the current to the circuit. In a series circuit, there is only one current, and that is the current to the circuit. So when the current through the circuit changes, the voltage across a fixed resistor is also going to change in the same behavior. So if the current in the circuit increases, the voltage across the fixed resistor is also going to increase. If the current to the circuit decreases, the voltage across the fixed resistor is also going to decrease. And that right there is going to give our answer for questions where we have to find how the voltage across the fixed resistor changes when the resistance of the resistance changing component changes. Cool. But what if the question goes one more step? What if it asks, how does the voltage across X change as well? We'll have to use the battery voltage. Now, in a series circuit, we know that the voltage of the battery is shared between its components. So the voltage across the battery, let's call it VB, is going to be equal to the voltage across the resistance, across the fixed resistor, plus the voltage across X. So if we want the voltage across X, it is going to be VB minus V1. Battery voltage minus the voltage across the fixed resistor. Cool. So previously, we already know what the voltage across fixed resistor, what happens to it. So if, let's say, the voltage across fixed resistor, it increases. Because there's a difference, the impact on the voltage across X is going to be the opposite of that. So if this guy increases, this guy will decrease. If this guy decreases, this guy will increase. When you're writing your explanations, you can simply write this. The voltage across the battery is equal to the voltage across the fixed resistor plus the voltage across the thermistor or the LDR or the variable resistor. You can just write that. And because it is a sum, if this guy goes down, this guy has to go up. If this guy goes down, this guy has to go up. You can just write like that. And that gives us our answer with regards to the change in voltage across the resistance changing component. And of course, you can also write battery voltage is constant, which is why when the voltage across the fixed resistor decreases, the voltage across the variable resistor increases. Something like that. And those 5 steps are the steps we're going to have to use to solve any kind of question when we are explaining the change to the circuit because of the change in resistance of the resistance changing component. Cool. Let's take a look at a sample question. So here we have a simple series circuit with resistor R1 and a variable resistor. And the question says the resistance of the variable resistor is increased. Okay, so because this is a variable resistor, we don't need to figure out how the resistance is going to change, unlike the resistor or an LDR. Cool. And the instruction is to explain the effect of that on the voltage across the fixed resistor R1, as well as the voltage across the variable resistor. So of course, we're going to start with looking at the total resistance. So because the resistance of the variable resistor has increased, so the resistance across this guy has gone up, the total resistance is also going to increase. Why? Because it is a sum. Next, we're going to look at the impact of that on the total current. Now, because the resistance has gone up, the current to the circuit is of course going to decrease. And we can now take a look at the fixed resistor because we have V is equal to IR and R is constant. So voltage is a direct proportional current. And because the current to the circuit has decreased, the voltage will also decrease. So the voltage across the fixed resistor will decrease because V is equal to IR, resistance of fixed resistor is constant. Okay, now that answers the first part of the question. What about the second part, the voltage across the variable resistor? Well, we just use the battery voltage. Battery voltage is equal to the voltage across the fixed resistor plus the voltage across the variable resistor. And if we want the voltage across the variable resistor, it is going to be different between the total voltage and the voltage across the fixed resistor. And because the battery voltage is constant, this guy has gone down, this guy will have to go up. And therefore, the voltage across the variable resistor has to increase. And that right there, my friends, is the answer for both of the questions. And these are going to be the explanations that we use. Now, for an exam question, it will usually stop with this much. This is like a 3-mark standard question. But sometimes if they ask for the voltage of the resistance changing component, you also have to go an extra 2 steps and determine how the voltage across that changes as well. And this is an intuitive approach that I like to use to recheck whether my final answer for the voltage across the resistance changing component is correct or not. Now in the circuit, right, the voltage is what pushes the current, and the resistance is a factor that is limiting the current. So when the resistance of that variable resistor or LDR or thermistor increases, the voltage has to work extra hard to push the current through the component. So if the resistance of the variable resistor increases, the voltage across that will also have to increase. Of course, you can't just write this in the exam. You only get like a mark for this. So you'll have to take these steps to get the full explanation marks. But I just like to think of this to recheck whether my final answer is correct or not. Okay, cool. And I have collected the question numbers and addresses of the questions for these two types of questions so that you guys can go and do the practice and see if the steps will work for these questions. And I'm confident that they will work because I used this same exact method when I was sitting for my national GCSE exams. Okay, so we'll do a couple of practice questions together, starting with a question from 2023 November paper 1P, question number 10. So here we have a circuit with a 5.8 volt battery and a 13 kilo ohm resistor in a series circuit. And we're going to change from this series circuit to this parallel circuit with an additional 200 ohm resistor. And we're going to have to explain what happened to the current in the 13 kilo ohm resistor and the current in the battery. So it's going to be the current through this. So starting with the 13 kilo ohm resistor, guys, please take a look. If you take a look, the 13 kilo ohm resistor still has the same path, and therefore the voltage across it is still going to be 5.8 volts. It's still going to be 5.8 volts. And the resistance of that guy is still 13 kilo ohms. And so if we take a look at our equation V is equal to IR, the resistance, 13 kilo ohms, voltage, still the same, and therefore the current should also be the same. So that right there is our answer for the 13 kilo ohm resistor, and it's going to score as 2 marks. Right, now what about the battery? Well, there will be a change in the battery. That's because we now have an extra path. So the battery is now working with 2 paths. Now, when we have 2 paths, remember guys, when we have 2 paths, we have more freedom. The electrons have more freedom with which to move. And because they have more freedom, the resistance that the battery is dealing with is going to decrease. And because there is a lower resistance, but the same voltage, 5.8 volts, the current is going to increase. Right? V is equal to IR. We're dealing with a lower total resistance, same voltage, and therefore current has to increase. And that right there is our answer for the battery current. The total voltage remains the same, but the total resistance reduced. And therefore, the current to the battery has to increase. And here is the mark scheme for this question. 2 marks for the 13 kilo ohm resistor and 3 marks for the battery. All right, let's take a look at the final question from 2022 June, paper 1P number 3. We're looking at a circuit where we have a thermistor and a fixed resistor with a voltmeter across it. And our instruction is to explain how the reading on the voltmeter changes when the temperature of the room decreases. And we're giving this diagram above in the question. So we're looking at the scenario where the temperature is going to drop. So when the temperature drops, the resistance of the thermistor is going to increase. So I'm going to say RT up. Okay, how does this impact the total resistance of the circuit? Well, the total resistance, I'm going to call this R sum, is equal to the resistance across the thermistor plus the resistance of the 140 ohm resistor. So this is going to be constant. but this guy has increased, and therefore the total resistance has to also increase. Okay, how does an increase in the total resistance have an impact on the total current through the circuit? Well, because the resistance is higher, the current through the circuit will decrease. So I is going to decrease. And now we come and take a look at the fixed resistor. Because we have V is equal to IR, this one is constant, the current has gone down, and therefore the voltage across the fixed resistor will also go down. And that right there is our answer. The resistance across the thermistor increases. Therefore, the total resistance increases. And therefore, current decreases. Because V is equal to IR and R is constant, the voltage across the fixed resistor will also decrease in proportional to the current. And therefore, the voltmeter reading will decrease. And I think this is going to give us a mark. This is going to give us a mark, and this right here is going to give us a mark in total of 3 marks. All right, guys, so this right here is a summary. We have the questions where we're changing from a parallel circuit to a series circuit and vice versa. And we have the questions where we are working with the fixed resistor and a resistance changing component such as a variable resistor, an LDO, or a thermistor. Okay, so I think I spoke quite, not quite, very fast in this presentation, but I hope that these steps really help you deal with these electricity questions because they do come up really frequently. And once you understand and remember the steps every year and every single question that you deal with is going to give you full marks. So it's going to really help you push towards that grade 9 that you're looking for. So yeah, that's pretty much it for this video. I have not been posting much because I've been really working with my own students, giving them really personalized feedback, giving them the time and attention that they need so that they can improve on their own mistakes. So I've not been having a lot of time to work on my channel, but I hope that for the upcoming exam on on June, so the physics exams for this series is going to be in June. I hope I can give you guys more videos and more revision tips so that you can ace the 2026 May-June paper 1P, 1PR, 2P, and 2PR. Okay, guys. Anyways, that's pretty much it. And as usual, take care, and I'll catch you guys in the next one. Peace.